Hey everyone, and welcome. Today we're going to pull back the curtain on the digital world. Have you ever just stopped and wondered how developers build these massive, complex apps we use every single day? Well, the secret is a philosophy called object-oriented programming, or OOP, and it's all built on 4 incredibly powerful ideas. I mean, seriously, think about it. Your favorite video game, that social media app you scroll through, even the operating system on your phone, they can have millions and millions of lines of code. How do they not just collapse under their own weight? How can huge teams of programmers all work on the same thing without it turning into total chaos? Well, the answer is OOP. Before this philosophy came along, programming was often, just a giant long list of instructions. It was messy. But OOP changed everything by organizing code around objects, which are really just digital stand-ins for real-world things. An object has data, which we call attributes, and it has actions it can perform, called methods. And these objects are all created from blueprints, or classes. This simple idea, bundling data and actions together, is what prevents all that chaos. And it all rests on 4 crucial pillars.
Okay, first up, pillar number 1, encapsulation. The best way to think about this is creating these secure, self-contained digital black boxes that package everything up nice and neat.
So what does that actually mean? Well, it means taking a piece of data, let's say your account balance in a banking app, and bundling it together with the only actions or methods that are allowed to change it, like a deposit or a withdrawal function. This little capsule protects that data from being accidentally changed or messed with from somewhere else in the code.
Your smartphone is the perfect real-world example of this. You interact with the screen, the buttons. That's the public part of it. But you can't just open it up and start messing with the processor or the memory chips, right? All that critical, complex stuff is safely encapsulated inside the phone's case.
And that leads us perfectly into our second pillar, abstraction. So if encapsulation is all about bundling things together, abstraction is about hiding all the messy details to keep things simple for the user.
The whole idea here is to only show what's absolutely necessary. You give the user or another programmer a really simple interface to work with while all the complicated logic is happening behind the scenes. This makes the code so much easier for other people to use and to understand.
Just think about driving a car. You don't need to be a mechanical engineer to go to the store, right? You just use the steering wheel, the gas pedal, the brake. The car abstracts away the thousands of complex things happening in the engine, which lets you focus on just one thing: driving.
Okay, so let's quickly clear this up, because this is where people sometimes get a little confused. Encapsulation is all about data protection, hiding the state of an object inside a protective shell. Abstraction, on the other hand, is about simplicity, hiding the complex how and just showing a simple what. One is basically a security measure, the other is a design principle to make things easier to use.
All right, let's move on to pillar number 3, inheritance. This one is a huge deal. It's all about being efficient and building on work that's already been done. It's basically the don't reinvent the wheel principle of programming.
Inheritance lets us create a new child class that just automatically gets all the properties and behaviors of an existing parent class. Then we can add new features or tweak the ones it inherited without having to start completely from scratch. It creates these really cool family trees of code.
Let's use a classic example to make this super clear. Imagine we create a general parent class called animal. We can say that every single animal has a name, a sound it makes, and a method called makeSound. This is our generic blueprint. Now check this out. We can create a more specific child class called dog. Since dog inherits from animal, it automatically gets the name attribute and the makeSounding method for free. All we have to do is specify what makes a dog unique. In this case, we'll just set its sound to woof. See? We've reused that entire base structure and just added one specific little detail.
And that brings us to our final and maybe the most mind-bendingly powerful pillar, polymorphism. It sounds super complicated, I know, but the core idea is actually incredibly elegant.
The word itself gives us a huge clue. Poly means many, and morph means form. So polymorphism literally means many forms. It's this amazing idea that we can use the exact same command for different types of objects, and each one will know how to respond in its own unique way.
So going back to our inheritance example, imagine we have a piece of code that just calls the makeSound method on any animal object. The code itself doesn't know or even care if it's a cat, a dog, a cow. It's totally generic. And this is where the magic happens. If that animal object happens to be a cat, that code produces meow. But if it's a dog, the exact same line of code produces woof. It's one command, but it has many different outcomes. That
Right there is polymorphism. It's so powerful.
Okay, theory is great and all, but let's see how these pillars actually hold up a real application. We're going to look at the basic logic behind a simple planetary weight calculator.
The goal here is super simple. Make a program that asks for your weight on Earth and which planet you'd like to visit, and then it tells you what you'd weigh there. It's just a fun way to see all these ideas we have been talking about actually work together.
So here's the basic flow of how it would work. First, we get the user's weight and their choice of planet. Then, the program looks up that planet's unique gravity data. Finally, it runs a quick calculation and shows the result. Now, it sounds simple, but notice how we're already treating each planet as its own object with its own special data.
This is exactly the kind of data our program would use. Each planet is an object, and its gravity constant is a key attribute. By using encapsulation, we've bundled this data point with the planet it belongs to. That keeps our program really organized, and importantly, prevents this data from being changed by mistake.
And boom, there's our result. You put in your weight, you select Jupiter, and the program uses Jupiter's unique gravity constant. The beautiful part is that the same calculation method works for any planet we give it. Thanks to polymorphism, that single method produces a totally different result depending on whether the planet object is Mars, or Jupiter, or Neptune.
So, when you boil it all down, what's the big takeaway here? These 4 pillars, encapsulation, abstraction, inheritance, and polymorphism, they aren't just academic rules. They are the fundamental strategies that allow developers to build the software we all rely on. Software that's organized, reusable, and that can actually be maintained and updated for years without completely falling apart.
So I'll leave you with this question to think about. Now that you know these core principles, where else do you see them? Think about the apps on your phone, or maybe even systems in the real world. Where do you see complexity being hidden behind a simple interface, or common designs being reused and adapted for very specific jobs? The architecture of good design is literally everywhere once you know what you're looking for.